Common ion effect. The common ion effect is an illustration of Chatellier's principle. Chatelier principle is an observation about chemical equilibria of reactions. It states that changes in temperature, pressure, volume, or concentration of a system will result in predictable and opposing changes in the system in order to achieve a new equilibrium state. So simply we can say that the system that is in equilibrium opposed to the change in, that is the external change, or also known as stress. So this stress can be in a form of temperature, pressure, volume, or concentration. For example, if we have an equilibrium reaction in which reactant A with number of moles of alpha is reacting with reactant B with number of moles of small b, and changes to two products known as C and D with number of moles of small d, C and D. So the equilibrium constant for this equilibrium reaction is equal to the product of the concentrations of products raised to power their coefficients, that are actually number of moles over product of the reactants raised to power their number of moles. At particular temperature, pressure, volume, and concentration, the value of equilibrium constant is a constant value for the particular reaction. For example, for this reaction, the equilibrium constant can be written as equation number, if this one is 1 and this one is 2. So from this equation we can see that if we change the concentration of any of the species, for example, if you are changing the concentration of oxygen, suppose we are increasing the concentration of oxygen, it means that this factor is increasing. In order to maintain the equilibrium constant value as constant, the system will go towards backward direction in order to make the concentration of N2O5 higher, so that the overall value of, or the ratio of this factor is equal to a constant value that was previous with previous concentration of 3 species. In order to understand the common ion effect, let's consider few points. Weak acid or weak base are partially ionized in water. It means that these species exist in a unionized form. It means that in the concentration of a solution, the species which are in molecular form have more concentration as compared to the ionized forms. The second point is ionic compounds like salts dissociate completely in the aqueous solutions. So there are 3 types of ionic compounds. So first one is the salts derived from strong acids or bases, like sodium chloride is a salt which is usually derived from the strong base and strong acid. Other type is strong acids and strong bases. Third type is completely ionizable amphoteric compounds. Here one thing is needed to remember, that the ionic compounds that are salts which are derived from strong acids or bases are completely neutral. When they are dissolved in water, they do not change the pH of the system, whereas the salts which are derived from weak acids or bases alter the pH of the liquid solvent. For example, salt of strong base, that is sodium hydroxide, and weak acid, that is acetic acid, is basic salt, whereas salt of strong acid is acidic salt. Now let's consider a question, that is, what happens if a salt is added to a solution of a weak acid and that salt contains a conjugate base to the weak acid. So now consider an example of a weak acid, that is acetic acid. As this is a weak acid, when it is dissolved into the water, it will dissociate into acetate ion and hydronium ion in the aqueous solution. And as this is a weak acid, the dissociation into ions is not 100%. It is less than 100% dissociation. Now we need to add a salt to this solution, and this salt must contain a conjugate base. Now let's take a salt, that is sodium acetate. So if you dissolve this salt into the solution which was obtained by mixing acetic acid and water, so what happens? All the sodium acetate molecules are divided into sodium ion and acetate ion into the solution. So this sign is showing that all the reactants are converted into product, but here we have an equilibrium. So the number of acetic acid molecules converting to acetate ion are equal to the number of acetate molecules converting back to the acetate ions converting back to the acetic acid molecules. So by observing these two equations closely, that what we have done, we have increased the conjugate base concentration without increasing the concentration of hydrogen ions. As the number of conjugate base, that is the acetate ion which is produced from the acid, is equal to the number of hydronium ions are produced. But with the addition of sodium acetate salt into this solution, we have increased the concentration of this conjugate base without increasing the concentration of this ion. And according to Chatelier principle, the equilibrium of the reaction 1 must shift to left. It means that we have excess number of conjugate bases that must go back to the molecular state or the acetic acid form in order to maintain the equilibrium constant. Now what happened? We will observe there is a decrease in concentration of this ion, which is actually concentration of hydrogen ion, as it is changing to water. As we know that the pH of the solution is negative log of hydrogen ion concentration. So in this case we have added a salt of weak acid that is the conjugate base, which is in common with the conjugate base of the this weak acid. Now come back to the equilibrium constant, that it should be of constant value. So by changing concentration of any of the species, in this case we are changing the concentration of species B, that is for example the concentration of acetate ion that is produced from the dissociation of the added acetate salt, but we have not added the hydrogen ions to the solution. So the hydrogen ions available in the solution will combine with acetate ions to make the reaction to move to left side. It means that the protons are combining with the conjugate base to make the acidic form, which means that the number of hydrogen ions are decreasing and overall decreasing the hydrogen ion concentration will lead to the increase in pH value. It means that the concentration of the acidic form or the unionized or undissociated acid is increased and less acid will dissociate. So this is the effect of the conjugate base to the weak acid is showing the common ion effect. So now what is the common ion effect? Common ion effect is the dissociation of a weak electrolyte that is decreased by adding to the solution of a strong electrolyte, that is a salt that has an ion in common with the weak electrolyte. Why this is weak? Because it is not dissociating completely into the ionic species, whereas this salt is dissociated completely into the ionic species. So the combination of a weak acid and the salt of strong base that have a common ion with the weak acid led to the decrease in the dissociative products of the weak acid, or alternatively we can say that the dissociation of the weak acid is further lowered. As this is weak acid, then the pH of the solution will be increased, means it become more basic and less acidic as compared to the condition when only this equilibrium condition was present. Now consider the example for numerical calculation. So for this reaction the Ka value is 1.8 10 to the power minus 5, and here Ka is actually an equilibrium constant. The concentration of acid solution in water is 0.5 molar. The equilibrium constant, that is Ka for the acid, is given as the product of the ionized species over undissociated species. Now let's consider 2.5 molar sodium acetate is mixed with the solution of 0.5 molar acetic acid. As the sodium acetate is a strong electrolyte which is ionizing completely to acetate and sodium ion, the concentration of the sodium acetate added was 2.5 molar. So the concentration of acetate ions produced will be 2.5 molar. Now again consider the reaction which is the dissociation of acetic acid. So let's consider X mole of acetic acid was used, which dissociated into X moles of acetate and X moles of hydrogen ions. So according to this rate expression, the rate equilibrium rate constant is equal to the expression given here before the addition of the sodium acetate salt, but after the addition we get the new expression, that is, if we consider the 0.5 moles of acetic acid which are dissociated into acetate ion and hydrogen ion, as the acid is a weak acid, the dissociation into ions is not 100%, so the rate expression become 0.5 minus concentration of ions generated, and with addition of this sodium acetate salt we have excess number of these acetate ions. So if we are using 2.5 molar sodium acetate, then it will generate 2.5 moles of acetate ion. So for this addition we have extra number of acetate ion which are 2.5 molar. So as in the previous case, which is the dissociation of 0.5 molar acetic acid into acetate and hydrogen ions, so here we have acetate ion which have concentration of X. So with addition of the sodium acetate salt, we have 2.5 molar acetate ions. So in common we have X molar acetate ions which are generated from the dissociation of 0.5 molar acetic acid, as well as 2.5 moles of acetate ion which is generated from the 2.5 molar sodium acetate. So overall we have X plus 2.5 moles of acetate ion, whereas the concentration of hydrogen ion is constant, which is actually generated from the acetic acid. So the concentration of the hydrogen ion will remain constant, that is X, whereas the concentration of the acetic acid is zero point 0.5 molar minus number of uh, acetic acid molecules that are dissociated into ions. So here we have 0.5, that was total amount of acetic acid minus number of acetic acid molecules which are dissociated. For simplification, these concentrations can be ignored because the contribution of these factors are very small, and addition or subtraction of these factors cannot affect overall value of the equilibrium constant. So we can reduce this equation to 1.8 into 10 to the power minus 5. This type of simplification is known as shortcut to the quadratic equations. So we can calculate the value of X, that is 3.60 into 10 to the power minus 6, which is actually the concentration of hydrogen ion. From the rate expression we can see that this X corresponds to the concentration of hydrogen ion, and from this concentration we can calculate the pH of the solution, that is equal to the negative log of hydrogen ion concentration, that is negative log of 3.60 into 10 to the power minus 6, that is equal to 5.44. Now let's take another example where the question is, what is the pH of an aqueous solution that contains 0.15 molar of ammonia and 0.05 molar of the salt, that is ammonium sulfate, which is actually derived from the sulfuric acid and ammonia. So in this example we have the equilibrium condition, that is the ammonia and which is dissociated into ammonium and hydroxyl ions, and the salt is dissociating into the ammonium ion and the sulfate ion. So here we have a common ion which is the ammonium ion. For this case we have equilibrium constant, that is Kb, is equal to the concentration of ammonium ion and the concentration of hydroxyl ion, and with respect to the concentration of ammonia, that is the weak base. So at start let's set the amount of ammonia that will ionize as the reaction goes to equilibrium. So the actual concentration of ammonia in this example is 0.15 molar, and let's X amount is dissociated into ammonium and hydroxyl ions. So In this case, we have to consider that the added salt is not directly altering the concentration of either ammonia or hydroxyline. Therefore, if X molar of ammonia is ionized, then the X molar of hydroxylines are produced at equilibrium, as well as X moles of ammonium ions will be produced. So the concentration of ammonium ion at equilibrium is equal to the amount of ammonia that is ionizing. So plus the added amount of ammonium ion from the salt is X plus 0.1 molar. That is the amount of the ammonium ions which are generated from the 0.05 molar ammonium sulfate. As one ammonium sulfate is generating 2 ammonium ion, the concentration of ammonium ion produced from the ammonium sulfate will be equal to the double amount of the 0.05 molar, that is the 0.1 molar. So if X number of ammonium ions are generated from the ammonia, so overall the number of ammonium ion will be equal to X plus 0.1, that is generated from the ammonium sulfate. Similarly, we will get the rate expression, that is the value of the equilibrium constant, that is 1.8 into 10 to the power minus 5. X plus 0.1, it is the amount of ammonium ion added through the addition of ammonium sulfate into concentration of hydroxyline over the concentration of ammonia minus the concentration of ammonia which is dissociated into the ions. Therefore, at equilibrium, the concentration of hydroxyline is 2.7 into 10 to the power minus 5 molar, and the ammonium ions are this concentration that is also generated from the ammonia, from this expression, the concentration of ammonium ion generated from the ammonia is equal to the concentration of hydroxyline, that is the X. So the concentration of ammonium ion will equal to 0.1 molar, whereas the concentration of ammonia will be 0.15 minus X is equal to 0.15 molar. So the POH is the concentration of the negative log of the concentration of hydroxyline, that is 4.57. So the pH will be calculated from the POH. pH is equal to 14 minus POH, that is 9.43. Similarly, if no salt was added, the concentration of ammonia, that is actually 0.15 molar, and the concentration that is dissociated, so overall concentration of ammonia is 0.148 molar. So the concentration of the species dissociated is equal to the concentration of hydroxyline and the ammonium ion. So POH for the concentration of hydroxyline is 2.979 and pH is 11.2. So here we have seen that the